Hey everyone! Welcome back to Chem Talk. In today's video, we'll be going over the various physical properties of alkanes. At the end of the video, you'll see just how important these seemingly inert compounds can be in biological systems and in medications. First, we should quickly remind ourselves of what physical properties are before moving on. Physical properties are characteristics of substances that, when observed, do not change the compound's identity. Some examples of physical properties include boiling point, melting point, density, solubility, and color. By boiling a substance, you do not change its chemical makeup. You are simply breaking the intermolecular forces that hold the compound's molecules together in a liquid state. Breaking intramolecular forces would result in a chemical change, which happens in chemical reactions. Now for alkanes. The physical properties of alkanes stem from their chemical bonds. Alkanes contain carbon and hydrogen single or sigma bonds. Because carbon and hydrogen have very similar electronegativities, alkanes are relatively inert or unreactive compounds. However, differences in physical properties can be seen within the alkane family. Take a look at the boiling points of unbranched or linear alkanes. Boiling points, or the temperature at which liquid alkanes change phase to become gaseous alkanes, are a result of enough energy being supplied to increase the speed of the molecules and break the intermolecular forces between them. In the case of alkanes, these intermolecular forces are called van der Waals interactions or London dispersion forces. In the world of ideal gases, these intermolecular forces are zero, but in reality, molecules still interact to a small degree in the gas phase. As the number of carbon atoms within the alkane increases, or when the molecular weight increases, the boiling point increases too. The first four alkanes, methane, ethane, propane, and butane, are gases at room temperature, or around 20 degrees Celsius, as you can see from their incredibly low boiling points. This is due to a smaller molecular surface area. In other words, the longer chain length results in more places for the molecules to interact with one another, increasing the van der Waals interactions or London dispersion forces. An increase in intermolecular forces leads to a more significant amount of energy needed to break them, shown as a higher boiling point. Alkanes with 5 through 16 carbon atoms are liquids at room temperature, and roughly from 17 carbons on, alkanes are solid at room temperature. This trend of chain length follows with other physical properties as well. As we move on, we can see that the melting points of alkanes also generally follow the chain length trend. Odd number alkanes, however, seem to have lower than expected melting points, and this can be due to less symmetry than their even counterparts. It's more difficult to pack together a large group of propane molecules compared to ethane molecules, resulting in propane having a lower, in this instance, more negative melting point. Because van der Waals interactions are very weak intermolecular forces, the melting points of alkanes are very low. In short, it takes very little energy to increase the speed of molecules to where they can move more freely. Increased molecular movement is a characterization of the liquid state. Now on to density. In this instance, we'll only be comparing liquid alkanes at 20 degrees Celsius against water, which we know has a density of 1.00 grams per milliliter. From the table, you can see that alkanes are less dense than water. This can mainly be attributed to water having a greater intermolecular force with hydrogen bonding, causing the molecules to be closer together, and because of water molecules having oxygen atoms, which oxygen atoms have a greater mass than both carbon and hydrogen atoms. Lastly, solubility of alkanes. You're probably familiar with the phrase like dissolves like. In most cases, this is true. At room temperature, alkanes, which are nonpolar due to the relatively nonpolar carbon-hydrogen bond, dissolve very little in water, which is a polar solvent. This is due to the thermodynamic unfavorability of the process. To put it simply, the energy that is required to break the intermolecular forces holding water molecules together is much greater than the energy that is released from the solvation or interaction between alkane and water molecules. Thus, the Gibbs free energy of the solvation would be positive or unfavorable. In the case of alkanes, dissolving in other nonpolar solvents, the standard free energy would be negative, representing a thermodynamically favorable process. As for branched alkanes, they too follow relatively similar trends in melting point, solubility in water, and density as their unbranched counterparts. They are virtually insoluble in water. They have low melting points due to their only intermolecular forces being van der Waals interactions, and they're generally less dense than water. However, something worth noting is the deviation of boiling points and melting points between branched and unbranched alkanes with the same molecular formula, otherwise known as constitutional isomers. In the instance of butane, with the molecular formula C4H10, and isobutane, also having molecular formula C4H10, the melting point and boiling point of butane is higher than that of isobutane. Butane's boiling point is almost 11 degrees Celsius higher than isobutane's, while its melting point is roughly 22 degrees Celsius higher. This is due to the shapes of branched molecules. It's harder to make a compact group of branched molecules like isobutane, leading to greater distances between the molecules, and as a result, less energy is required to melt the solid. As for boiling points, a more nonlinear shape results in less surface area. With a greater surface area, more interactions can occur between various molecules, leading to greater overall van der Waals interactions or intermolecular forces. Since butane is a more linear molecule, in the solid state its molecules can pack closer together, leading to a greater amount of energy needed to separate them, shown as a higher melting point. Also due to its linear shape, butane has a greater surface area than isobutane, so butane's molecules are able to interact more with one another, increasing the van der Waals interactions between them. Some special cases can be observed, though. Symmetry in branched alkanes, like in the different isomers of hexane, can actually increase melting points while also decreasing boiling points. This is due to better packing of the individual molecules. By getting closer together, more energy, represented by a greater temperature, is required to increase the speed of the molecules to a point where they move more freely in the liquid phase. Exceptions to the branching trend in relation to melting points aren't very common, and if you are asked to make comparisons, they'll usually be made against different constitutional isomers for simplicity, meaning they'll have the same molecular formula. Finally, let's look at how some physical properties of alkanes can explain important processes in everyday life. You're probably familiar with phospholipid bilayers. These bilayers are important to every cell in your body because cell membranes are composed of them. Phospholipids consist of a hydrophilic head as well as two hydrophobic tails. Have you ever dug into exactly why the heads and tails of phospholipids are hydrophilic and hydrophobic? It's due to the types of bonds and atoms that make up the different parts of the phospholipids. The head of a phospholipid consists of a negatively charged phosphate group as well as a glycerol group. Due to their polar bonds and atomic makeup, these groups have a high affinity for other polar substances such as water. As for the hydrophobic tails, they consist of fatty chains, otherwise known as hydrocarbon chains. These tails are made of alkanes, which are nonpolar in nature because of the nonpolar carbon-hydrogen single bonds. This is why small, nonpolar molecules and compounds are able to passively diffuse through a cell membrane. The molecules in high concentration outside of the cell are essentially dissolved by the hydrophobic tails of the bilayer and then pass into the cytoplasm where they are in lower concentration. Large polar molecules thus need to be facilitated via intramembranous proteins because the net change in free energy for the process would be positive, or the process is thermodynamically unfavorable and an input of energy is needed. Alkane's relative unreactivity is also vital for medications. Many drugs have alkane or alkane derivative backbones in addition to highly reactive functional groups such as carboxylic acids, esters, amines, and amides. These alkane backbones allow for stability of the molecule. Since the carbon-hydrogen bond is incredibly strong, it would be difficult to damage medications via this route. A few examples of medications with alkane backbones or derivatives include perindopril, an ACE inhibitor used to treat hypertension and other cardiovascular issues; ethane sulfonic acid, which is a medication with various uses such as cancer treatment and bowel disease treatment; and mavorixafor. an anti-HIV fusion inhibitor drug. All in all, let's summarize what we went over about alkane physical properties. Alkanes are generally inert compounds. This is due to the nonpolar CH sigma bonds that they consist of. The physical properties of alkanes stem from the weak van der Waals interactions between individual molecules. The greater the number of carbons in the linear alkane, the overall higher melting point and the higher the boiling point. This is due to increased surface area and in turn greater van der Waals interactions. Branched alkanes, on average, have lower melting and boiling points than unbranched or linear alkanes. This is because of decreased surface area, leading to weaker van der Waals interactions. Since alkanes are nonpolar molecules, they dissolve best in other nonpolar molecules due to favorable changes in free energy between the solute and solvent molecules. That's all we have for today. For more chemistry fun, please visit www.chemistrytalk.org. Thank you.